everyone. Today we're going to be looking at a different type of differential equations where the variables aren't separable. So a definition first. A first order differential equation. Now remember, first order means that it is just using first derivatives. So we don't have any second derivatives in these. And a first order differential equation is considered homogeneous if we have, so dy dx is some function of x and y, but it can be rewritten as some function of y over x. So we can rearrange so that we have a y over x kind of scenario, in which case we can do a substitution of v equals y over x, and we can go from there. So if I look at an example of this, initially I have this written as x squared times dy dx equals xy plus 3y squared. But if I divide everything by x squared, then what I get is dy dx equals y over x plus 3y squared over x squared. So I'm going to write that as y over x all squared. So in other words, I can rearrange this so that while I can't separate the variables here, you can play around with that and try if you want, but it's not really doable. I can rearrange it so that it is an expression of y over x. This allows me to do the substitution. So I can sub v equals y over x, which is equivalent to y equals vx. And that's important for the derivative part because I can't just substitute y over x if I still have dy dx and then an expression in v. That's not helpful in terms of separating variables. But because of the the product rule of derivatives, I know that this means dy dx equals v times dx, which is just 1, plus x times dv dx. So I can do the substitution of y over x for v, but I can also do the substitution of dy dx for v plus x dv dx. So in other words, now I have v plus x times dv dx equals v plus 3v squared. And this actually is separable now. Conveniently here, the v's are going to cancel off. So I have x dv dx equals 3v squared, which I can now separate x and v. So I get 1 over v squared dv equals 3 over x dx. And now this is a separable differential equation. So now I can integrate both sides with respect to the variable on that side. And I get negative 1 over v is the antiderivative of 1 over v squared equals 3 ln of the absolute value of x plus some constant. I can actually consider this constant. So let's say this is ln of some other constant. That means this is the ln of cx cubed. And I'll just make the whole thing absolute value. The c can be positive or negative. In that case, it doesn't really matter. And then I get, when I isolate for v equals negative 1 over ln of cx cubed. I don't actually want v, I want y. So y over x equals negative 1 over ln of cx cubed, which means that y equals negative x over ln of cx cubed. So that is the basic idea here. If I can rewrite my function or my differential equation so that the derivative is a function of y over x. That's the only substitution you need to know offhand. Occasionally you'll come across a question where a different substitution is necessary. In that case, you would be told the other substitution. But generally speaking, when we're talking about homogeneous equations, we're talking about a substitution of v equals y over x specifically. So let's look at a couple more examples. So we've got another one where we've got dy dx times x squared this time. Again, if we divide that out, usually we'll do this so it's not immediately obvious that it's y over x. So you would be seeing an equation like this and you wouldn't necessarily know offhand that it's not separable. So you might try that first because that's usually the easiest thing. You're going to have to play around with some manipulations. Next week, we'll look at a different type of differential equation where we have to solve it using integrating factors. And it definitely becomes more complicated when you don't know what type you're looking at. What that comes from is tons and tons of practice. So if you've practiced a bunch of separable differential equations, you get better at recognizing which ones aren't separable. If you've practiced a bunch of homogeneous, you get better at recognizing which ones are not going to be able to be rewritten as a function of y over x. In this case, knowing that if I divide by x squared, I'm going to get dy dx equals y over x all squared plus 4y over x. So again, I'm going to do that substitution. Now, I never remember off the top of my head. I remember that v equals y over x. I don't remember off the top of my head what I'm going to substitute dy dx for. It is always going to be v plus x dv dx. But I don't bother memorizing that. I just think of it, oh, okay, it's the product rule. And so I'll quickly do the product rule off to the side. So that means that dy dx equals v plus x dv dx. Now, whether you write that or not, that's kind of irrelevant. It's something that you're expected to know. So now I can come over and do the full substitution. So I've got v plus x dv dx equals v squared plus 4v, which means I have x dv dx equals v squared plus 3v. And this is now separable. So I've got 1 over v squared plus 3v dv equals 1 over x dx. That left-hand side's easy. The right-hand side is going to require some partial fractions. So I've got something over v plus something over v plus 3. Oops, shouldn't be the same something. Is going to equal 1 over v squared plus 3v, which means that AV, don't know what just happened there, AV plus 3A plus BV equals 1, which means A plus B equals 0, and 3A equals 1. A therefore has to equal 1/3, and B has to equal negative 1/3. So what that means for the integral, if I'm integrating both sides of this differential equation, which has now been separated, is that I have, well, I'll write out the full. So I've got 1 over 3v plus 1 over 3v plus 3, sorry, minus 1 dv. On the other side, I already know that it's ln of the absolute value of x plus some constant. Although typically, like we did in the previous case, I'm going to choose to write this as ln of cx. Just for simplicity's sake. On this side, I get 1/3 ln of v minus 1/3 ln of v plus 3 is ln of cx. I can combine this side. So using log laws, these are both now going to be essentially cubed roots. So I've got ln of the cubed root of v over v plus 3 equals ln of cx. But now that it's just ln on both sides, I can let that drop. So I've got the cubed root of v over v plus 3 equals cx. I'm going to also drop the absolute values at this stage because that's a nuance I talked about before that we're not going to really focus on too much. Actually, I'm going to call that a C2 because when I cube this, I'm going to just make it a different constant. So I've got v over v plus 3 equals some new constant x cubed. I do still want to isolate for v before I bother substituting for y. This becomes a little too complicated. We're going to just, this question is taking more space than I had anticipated, so I'm going to introduce a little more space. If you can see this next question now, when we're done this one, if you want to pause and maybe practice that next question before we go on to the solution, then by all means do that. So isolating v here is a little bit tricky, but not too bad. So I get cx cubed v plus, oh, I'm going to call that c3, because now when I multiply it by 3, it's just some new constant. So actually, these are two different constants. You know what? Rather than have two different constants, I'm going to keep 3c. Yeah, that'll do. So v minus cx cubed v equals 3cx cubed, which means I've got this whole thing, a little bit lengthy, but we're getting there. 1 minus cx cubed. Now, since v equals y over x, this now means that y is just x times that. So 3cx to the power of 4 over 1 minus cx cubed. There we go. Took a little while, but we did get there. All right, so now if you wanted to take some time and practice this next one before we go on, by all means do that. But again, we're going to look to isolate the dy dx so that we can see if it can be expressed. Of course it can, that's the point of this section. So if I divide everything by xy squared, I get dy dx, oops, plus, so here I get x cubed divided by xy squared, which is x squared over y squared, equals y over x. Oh, hold on. So we've got dy dx equals y over x minus x squared over y squared. I'm going to actually write that as, so I've got y over x, and I've got y over x to the power of negative 2. So that's because I'm looking for y over x, not x over y. So then I do the same substitution as I've done before. So v equals y over x, which means dy dx equals v plus x dv dx. So we've now got v plus x dv dx equals v minus v to the power of negative 2. The v's are going to cancel off here. So we've just got negative v to the power of negative 2, which means I've got, it doesn't really matter which side I put the negative on, so I'm going to do it this way. All right. And then we integrate both sides. We've got v cubed over 3 equals negative ln of, and I'm just going to kind of skip ahead here to cx, where c is some constant. So the plus c would have just been some logarithm of something, and so going from there. That means that v cubed equals negative 3 ln of cx. So v equals the cubed root of negative 3 ln of cx, which means that y equals x times the cubed root of negative 3 ln of cx. There we go. And finally, we're going to do one with an initial condition. So again, if you want to pause the video right here and have a look and see if you can play around with that and figure out what it would be, then go for it. The only difference between this question and the previous ones, I'm telling you x is positive, so we can avoid the absolute value. We don't need to worry about it. And I'm giving you an initial condition. When x equals 1, y equals 4. So dividing everything by x squared, I'm going to get dy dx equals y over x squared minus y over x plus 1. So our usual substitution, we've got a y over x. So I've got, oops, jumped down. I've got v equals y over x, which means dy dx equals v plus, oops, stylus is being weird, as usual, x times dv dx. Now again, you do not have to write that at the side every single question. However, you might find yourself doing a worksheet or a quiz or a test at some point where you've got a bunch of different differential equations and they're not all the same type. So in order to indicate, okay, this one is homogeneous, this is the substitution I'm doing. So I've got v plus x dv dx equals v squared minus v plus 1, which means that I've got x dv dx equals v squared minus 2v plus 1, or just v minus 1 all squared. That's going to be easier to integrate. So I've got 1 over, actually, I'm just going to write it with the instead of 1 over, I'm going to write it with the negative exponent. So I've got v minus 1 to the power of negative 2 dv equals 1 over x dx. The reason I'm doing the left-hand side with the negative exponent is to remind myself, oh, okay, this is just a power rule situation. And because the v minus 1 just has a derivative of 1, I can just very simply say that the antiderivative here, okay, so I'm integrating both sides. So the antiderivative of that left-hand side is v minus 1 to the power of negative 1 divided by negative 1, and ln of x plus c, but I'm just going to make it some different c of x. And again, do not need the absolute value because I've told you that x is greater than 0. This now means that, all right, sorting that out, let's put the negative on the right-hand side. So I've got 1 over v minus 1 equals negative ln of cx. That means that 1 over negative ln of cx equals v minus 1, which means that 1 over negative ln of cx plus 1 equals v, which is y over x. So we've got y equals x over negative ln of cx plus x. And here's where we can figure out. So you could have figured out it a little earlier. If I was figuring it out before I substituted y over x back in, then I would have to, it's not too complicated, knowing that v equals y over x. If y is 4 and x is 1, then v is also 4. But let's substitute that in right now. So y is 4, x is 1. So just very quickly, 3 equals 1 over negative ln of c. So ln of c equals negative 1/3. So c equals e to the power of negative 1/3. That then means that what we've got, so I've got y equals x over negative ln of e to the negative 1/3 x plus x. You can leave it this way, or you can use the log law if you like to separate that e to the negative 1/3 out again, but it's probably easier just to leave it this way. And that's basically it for this question. So you can see most of it here. There's exercises that you can use to practice these in that option PDF. It's section 5.4 of that PDF.